I will present some aspects of reinforcement learning algorithm in finance, and more precisely, I will speak about portfolio allocation and through the policy gradient approaches, which is a joint work with Pierre Brugière from Université Paris-Dauphine. As a short summary, reinforcement learning algorithm managed to do very well in different tasks and can manage to deal with available information. However, there are not so many applications in finance, and I will use some flow gradient approaches to propose an algorithm. And it will also take into account some transaction fees. And as a disclaimer, this is just research, do not invest based on that. There are many types of learning. Can be supervised learning, which is this left image here, when you have some images and you try to say that this is a horse, this is a truck, this is a deer, and so on, this is a car. So you just assign labels. Here in the middle is generative learning, where you base, for instance, on a prompt or whatever, and you create a new object. And we will be concerned about this reinforcement learning, and I will just, in order to have a visual image, this is what is done. So do you see this video? I hope.
Yes, we do.
Well, it's Pac-Man that tries to win white dots, and well, this is an algorithm that tries to learn this game. Now I can put in full screen. I hope it will work. Oops, it does not work so good. Okay, in reinforcement learning, there are many toy examples, like in any other research domain. And here, the multi-armed bandit is a toy example. Here, what is the multi-armed bandit framework in reinforcement learning? You have K options to choose from. For instance, you have to, this comes from Las Vegas machine, that you have to choose which one will make you rich. And here, so you have to allocate limited resource, which is time or money or medical treatments or whatever, in order to maximize expected rewards. So each time you have an action to do, here the action will be denoted A, for instance. The action has a reward, which is of unknown means. You don't know which one is the best. And it has a mean value, an average value that you don't know and you want to discover. And this is important, the part of the reinforcement learning, that is the statistics are unknown, starting with the average. And the R would be the reward, A will be the action chosen at time T, and T here, well, it's not really continuous. It's one step to another, one action to another. It is the part that I will present, it will concern a policy gradient algorithm that can be written as a probability law. Actions are chosen depending on a probability law pi t, which changes with time, which is learned. And probability to choose action A is pi t of A. And pi t of A, it's a number, a positive number, that when you have k choices that sum up to 1, which one is positive. And it's not very easy to work with this kind of objects because, well, there are many constraints, they are positive, sum to 1, and so on. And people like to work with very free variable, which are the logarithm of pi, which are called here h, up to logarithm up to constant, and introduce the softmax function. So h gives pi with this formula. It's exponential of h over overall factor. Okay, so these are the new variables. You can derive the pi with respect to h. This is easy to find formula. And so you can obtain the gradient of your reward. The reward is here, the unknown average times pi. And you can start a gradient descent algorithm. And this one, among others, is called policy gradient descent algorithm, which updates the age, which are the new variables. These are the old one, depending on the reward that was obtained. It is customary to also add some baseline bar, which is the average of rewards obtained so far. And this is just a gradient algorithm written for these variables. You know that there is a learning rate alpha, which nobody tells you what to which values should be set. And in practice, it may be difficult to get the right one, and you have to search for several until you find a good one. What is the final setting I will present is a portfolio optimization as you choose between K assets. Well, here you can even combine them. So it's a little bit more different than just the multi-arm bandit. If you take a portfolio composed of a pure asset, just one of the assets is exactly the multi-arm bandit. But if you can combine them, well, it's a little bit different. I will write the formula right away, but it's not so far. What is important is that if you know in advance for the year to come, for instance, what are the statistics of the rewards, which will be the return for each asset, and their correlation and so covariance metrics. And there is a classical Markowitz portfolio theory that tells you which is the good portfolio repartition allocation to choose, depending on your risk propensity. But in general, the future is unknown. And so these statistics are not it's not reasonable to suppose you know them. Of course, well, the past is some kind of give some indication on the future, but it's not so easy to predict. And moreover, in this theory, and as in many others, the misspecification had a huge impact on the result. And if you don't have the right values, you may end up losing very much. So you have to learn this kind of statistics, the average of the reward that you will obtain from each asset and so on the fly. So this is where the online portfolio selection comes into play. And I put here a pointer to review. Besides reinforcement learning, there are other approaches. For instance, the Cover Universal Portfolio. Olmar is very related to reinforcement learning and so on. Notations here. So PyT, I will work with a portfolio that cannot short sell assets. So the proportional wealth allocated to asset K at time K is positive. So it's a PyT of K, so proportion, and they sum up to 1. And the price here, the price of the asset K, will evolve with a multiplicative factor F. So the price yesterday multiplies by F to obtain the price today, and the price today multiplies by FT plus 1 to obtain the price of tomorrow. So these are the multiplicative factors that govern the evolution of the assets. Of course, they are unknown. They are known from the past, but the future is unknown. And they have a name. So these are the price relatives. FTK minus 1 is known as the return of the interval. So when you look at the financial data, I don't know what index rose 10%, this is the return. What is how the value of the portfolio changes from T to T plus 1? Well, if the value was W, then the new value is pi, scalar product of pi times F. And this multiplies initial W, and from time 0 to time T plus 1 is just a product of these scalar products. And you have to maximize this total wealth. When you maximize function, these are pi k are elements in a complicated space. I will come back to that. So either you maximize or minimize, you have to optimize some functions on a complicated space. So you will see that are concerned with probability, as we already said, we are concerned with probability laws, and they live as a metric space, not in a Hilbert space. And there is, you want to, for instance, if you want to minimize a function in a f of t in a metric space, you can imagine a gradient flow, but the gradient flow would have this equation, x prime of t equal minus gradient of f. But here in a metric space, you don't have any minus. And it's difficult to write such an equation. And there is a huge literature explaining how to write gradient flows in metric spaces. I will not enter this into detail, but one of the numerical schemes that are used, Jordan, Kindler, and Otto, explains that in order to do this, you can advance from xn to xn plus 1 by minimizing that, which means that you minimize f, which is your goal anyway, staying close to a previous x. And if you look at this as optimization problem in a Hilbert space, we see that, in fact, this is an implicit Euler scheme, because this will be the norm of x minus xn. When you do the gradient, you obtain this equation. So it's just an implicit Euler. So with this kind of idea, you can generalize flows to the metric spaces. So let's come to our example. So you want to maximize final wealth. You have h, your variable here, and pi is the softmax of h. And I will pass from pi to h very fast. So I will not write the function as explicitly too much. Minimizing wealth or its logarithm is the same, so it's easier to maximize, in this case, the logarithm. So in fact, we want to maximize at each step. This is your reward, let's say, for the at step at time t or time k here. And I will not enter into detail, but sometimes you want not only to maximize your reward, but minimize the risk. And this I will not discuss. Time does not allow to do everything. So you want to maximize that f of h. The GKO approach would tell you, well, just minimize the distance from the previous one minus function f. Well, if this is true, but you may also want, for instance, to treat transaction costs. Just as a side remark, from yesterday, the portfolio allocation imagines that one of the assets just broke down. It's failure. Price is 0. So the allocation is now 100% and the one that's left. So you see that there is a drift induced in the composition of portfolio just because the price changes without you doing anything. So in order to compute transaction cost, for instance, this drift has to be taken into account. And you have, for instance, if you want to penalize transaction cost, you have your new allocation or target new allocation. The transaction cost is the sum over this absolute values difference from the previous one to the next one. This may be a function difficult to optimize, but one can imagine regularizing that. Okay, so let's summarize. We have at each time step t some factors given by the market. We have no control over them, and we have to maximize f and minimize transaction costs. These are the two formulas, which can be written as minimizing g minus f. If we use the GKO idea in order to advance from ht to ht plus 1, ht plus 1 should be a minimizer of that distance square over 2. This is the time step, and plus the sum of the functions to be minimized. And so you solve this kind of equation. Well, there are ways to solve approximately this equation by using a first order approximation in tau. It is good for small tau. This is the same as the explicit Euler scheme. but it's not good for large too. It may be unstable. And the question is, in our case, tau, is it small or is it large? But this tau is just an auxiliary of computation. We don't know what is its value. So it may be large, it may be small. And in practice, it turns out that we want to make it rather large sometime. Why? Because the data, we don't have enough data, and we want to use data as long as possible. So we will use it to evolve age. So this tau may need to be set to large values. So we may use long time step tau, and in this case, it's better to use implicit schemes. Implicit schemes are exactly as just solving this gradient with respect to age equation, but is a really complicated equation. You see, there are many functions and so on. There's no explicit solution to this implicit equation. But a way to solve it is just to recall that this is a gradient flow finally. So just follow this gradient flow. The number of assets here is not so huge. Maybe 2, it may be 10. Dow Jones has 30 assets, the S&P 500 has 500, and that's all. So it's finally an ODE, maybe in a fairly large dimensional space, but it's not finally so large. So you can solve this as an ODE. And this is what we do. This is our proposal to not try to do explicit schemes which may be unstable. And as it always the case in reinforcement learning, we can add some baseline. So this is our numerical scheme. This is a multiplicative factor taking into account the transaction costs. These are the part that coming from maximizing the rewards. And if you see, well, this is not very, very different from what people use in the literature. They use an approximation which turns out to be very close to ours, except when there are transaction costs. As a numerical, this is the numerical algorithm, but what about the theoretical side? So there are two regimes. So first, the regime where the transaction costs are large, they have a huge impact on the performance. So when Xi is large, finally in the terms here, the G part is important, is penalizing, and it turns out that J can be seen as a Huber energy distance. And it turns out that in this case, well, you obtain a gradient flow, but in some metric space related to the Huber energy metric. When on the other side, Xi is 0 or very close to 0, you obtain this kind of flow, but with f of t, the changes as piecewise constant. I am coming to numerical results to close the presentation. So these are numerical results. I took some benchmark from the literature. They are I put here in red because in finance people try to get rich right away. So, well, these are the benchmarks. So I don't say anything about what will happen tomorrow or another situation. Anyway, there are two assets here from one of the benchmarks, the cover universal portfolio benchmark. So the assets that you see here is the blue one and the orange one. And the cover portfolio is in green, and what you obtain is in red, because of course you present results which work, and it does work for this benchmark. And to the right hand side is another one, and in this case one asset had not much performance, and both algorithm universal portfolio and ours understood that, and you see that both move in synchronicity with the other asset, which is the blue one. And of course, we tell nothing. We just feed data to algorithm. We tell nothing about the future. Okay, so it's a little bit better than the universal portfolio. And so it's at least competitive with present result from literature. And What about transaction fees? Well, here, this how to understand this plot is the same as at the left here. So these are the two assets, and they are combined. It may be counterintuitive that combining an asset that have a reward about 8, you obtain a reward of 40, but it is possible. And you see the transaction cost lower this. If this is the efficiency if you don't take into account transaction costs, and our algorithm more or less close to cover. And if you take into account transaction costs, the cover algorithm does not compare favorably with the assets. There's just more or less the average of them, while in our case, we still keep some gaps. So there is an advantage, even if transaction costs are large to use it. And I thank you for your attention. And there are some references, and I will put this on the webpage, the slides, in case you need it. Thank you. If there are any questions, I'm happy to answer.